Imagine standing on the coast of Spain looking east toward Italy, but instead of seeing endless blue water stretching to the horizon, you're staring into a chasm, a void so deep it makes the Grand Canyon look like a ditch. The Mediterranean Sea is gone, completely gone. And at the bottom of this massive basin, almost 2 miles below where you're standing, there's nothing but blinding white salt flats, shimmering in the heat, stretching farther than your eyes can see. This actually happened. 5 to 96 million years ago, the Mediterranean Sea didn't just dry up a little, it vanished. The entire thing evaporated into the atmosphere, leaving behind a hellscape of salt deposits thousands of feet thick, and temperatures that would make Death Valley feel like a vacation resort. If you're using this to fall asleep, that's literally why I make it. So subscribe maybe, and tell me where you are and what time. I check comments, and it's like Sydney at sunrise, Seattle in the middle of the night all at once. It's wild to think we're all here together, separated by thousands of miles and a dozen time zones, learning about a flood that happened before humans even existed. Now here's where the story gets insane. That dry Mediterranean basin didn't stay empty forever. 600,000 years after it dried up, something happened at Gibraltar. The thin barrier of rock separating the Atlantic Ocean from that massive desert valley finally gave way. And when it broke, the result was the most catastrophic flood in Earth's geological history, the Zanclean Flood. We're not talking about a river overflowing its banks or even a dam breaking. We're talking about 90% of all the water flowing on Earth's surface suddenly being diverted through a single channel. A waterfall that would dwarf Niagara Falls by a factor that's almost impossible to comprehend. A torrent so powerful it could fill the entire Mediterranean basin. A body of water containing 1 million cubic miles of water in less than 2 years. Scientists call this the Messinian Salinity Crisis, and it's ending. The Zanclean Flood. But those sterile academic names don't capture the sheer apocalyptic scale of what happened. This wasn't just a geological event. It was Earth fundamentally reshaping itself in the most violent way imaginable. And here's the really mind-bending part. Nobody knew this happened until the 1970s. For centuries, scientists looked at the Mediterranean and just assumed it had always been there, always filled with water, always connecting Europe to Africa and the Middle East. Why would you think otherwise? It's the Mediterranean. It's permanent. It's been there forever. Wrong. The story begins with an oil company. In the late 1960s, petroleum geologists were drilling core samples from the Mediterranean seafloor, looking for potential oil deposits, standard exploration stuff. They're pulling up ancient sediment layers, analysing them, trying to understand the geological history of the region. Then they find something that makes absolutely no sense. Buried under thousands of feet of normal marine sediment, there are layers of gypsum and halite, salt deposits, massive ones. The kind of salt formations that only form in one specific environment, shallow evaporating pools in scorching desert conditions. At first, they think it's contamination or a mistake. Because these salt layers are sitting at the bottom of the Mediterranean Sea, under 10,000 feet of water. Salt deposits like this don't form underwater. They form when water evaporates away completely, leaving behind dissolved minerals in thick, crusty layers. But the evidence keeps mounting. Core samples from different locations all show the same thing: salt layers, sometimes over a mile thick, buried under normal seafloor sediment. The geological community is baffled. How do you get desert salt deposits at the bottom of an ocean? Then a geologist named Kenneth Shue puts together the impossible answer. The Mediterranean didn't always have water in it. About 6 million years ago it was a desert, a massive continent-sized basin filled with nothing but salt and heat and death. When Sue first published his findings in 1973, other scientists thought he was crazy. Drain the entire Mediterranean Sea? The whole thing? That's not how geology works. Oceans don't just disappear. But the evidence was undeniable. The salt deposits, the fossils of desert plants found in sediment cores, the weird erosion patterns carved into bedrock that could only be explained by rivers cutting through exposed rock when sea level was thousands of feet lower. The Mediterranean had dried up, and then, catastrophically, violently, it refilled in one of the most dramatic geological events in Earth's history. Over the next hour or so, we're going to explore exactly how this happened. How a sea that's been a constant presence in human civilization for thousands of years completely vanished millions of years before humans even existed. How entire ecosystems were wiped out and then reborn. How the Atlantic Ocean punched through Gibraltar with enough force to reshape continents, and how the evidence of this ancient catastrophe is still visible today if you know where to look, in the rocks beneath Mediterranean cities, in the salt mines of Sicily, in the underwater canyons carved by rivers that flowed when the seafloor was a desert valley. So get comfortable, let the story wash over you. And let's go back 5.96 million years to when the Mediterranean Sea began to die. 5.5 million years ago, if you could stand on the shore of what we now call the Mediterranean Sea, you'd be looking at something completely different from the vacation destination you know today. This wasn't the sun-drenched sea of modern cruise ships and beach resorts. This was the late Miocene Mediterranean, and it was spectacular. Picture this. An enormous basin stretching from the Atlantic coast of Spain all the way to the Middle East, nearly 5 million square kilometers of open water. But here's what makes it fascinating. This sea wasn't just big. It was alive in ways that would seem almost tropical today. The water temperatures were several degrees warmer than modern Mediterranean temperatures. The coastlines were fringed with vegetation that would look more at home in Southeast Asia than modern Europe. And the waters teemed with life forms that would make a modern marine biologist weep with joy. Because the Mediterranean you're imagining, it wasn't some isolated backwater. It was the westernmost remnant of something far grander, far more ancient, the Tethys Sea. Now, the Tethys Sea is one of those geological features that sounds made up, like something from a fantasy novel, but it was real, and it was enormous. For hundreds of millions of years, from the time of the dinosaurs all the way through to the age of mammals, the Tethys Sea stretched from the Atlantic Ocean clear across to the Pacific. It was the great seaway that separated the northern continents, Laurasia, from the southern continents, Gondwana. When Africa was still attached to South America and India was an island floating northward, the Tethys Sea was the vast ocean between continents. But continents don't stay still. That's the thing about plate tectonics. It's slow, but it's relentless. Africa, freed from its attachment to South America, began drifting north. Slowly, so slowly you couldn't see it in a human lifetime, but fast in geological terms, about 5 centimeters per year, which doesn't sound like much until you multiply it over millions of years. Then it becomes thousands of kilometers of movement. As Africa pushed northward, it began colliding with Eurasia. This wasn't a sudden crash. It was more like 2 massive floating rafts slowly crunching together for millions of years, and caught between them was the Tethys Sea. picture it like a massive ocean being squeezed into a smaller and smaller space. The eastern portions closed first, the collision between Africa, Arabia and Eurasia creating the Alps in the north, the Zagros Mountains in the east. What had once been seafloor was thrust upward, becoming some of the most dramatic mountain ranges on Earth. By 5.6 million years ago, only the westernmost portion of the Tethys remained. That was the Mediterranean, but it wasn't isolated yet. It was still connected to the Atlantic Ocean through a strait at Gibraltar, and that connection made all the difference. Because here's the thing about the Mediterranean geography. It sits in a region where evaporation exceeds rainfall. This is basic physics. The sun beats down on all that water, evaporating it into the atmosphere. Some of that moisture falls back as rain, but not enough. Not nearly enough. Modern calculations show that the Mediterranean loses about 4,000 cubic kilometres of water to evaporation every year. That's more water than all the rivers draining into it, the Nile, the Rhone, the Po, the Danube, can replace. So without that connection to the Atlantic, the Mediterranean would dry up in about 1,000 years. Just gone. A giant empty basin where an ocean used to be. But 6 million years ago, that connection was wide open. Well, relatively open. The Strait of Gibraltar was probably several times wider than it is today, maybe 20 or 30 kilometres across at its narrowest point. And through that strait flowed something essential: replacement water. Every year, massive amounts of Atlantic water poured into the Mediterranean, replacing what evaporation had stolen. This created a circulation system that kept the Mediterranean alive, kept it salty at normal oceanic levels, kept it connected to the global ocean ecosystem. And what an ecosystem it was. The fossil record from this period, preserved in sediments that were once Mediterranean seafloor, tells us about a marine environment that was astonishingly diverse. We're talking about whales, multiple species of them. Baleen whales that filtered vast quantities of plankton from the productive Mediterranean waters. Toothed whales, early ancestors of modern sperm whales and dolphins, hunting fish and squid in deep water. Sharks were everywhere, not just a few species, but dozens. Great whites, ancestors of modern white sharks, patrolled the open waters. Megalodons, those monster sharks that could grow to nearly 20 meters long, probably cruised the deeper regions, hunting marine mammals. Smaller species filled every available ecological niche. Bottom feeders, mid-water hunters, coastal predators. The fish diversity would have rivaled modern tropical seas, ancestors of modern tuna, groupers, sea breams, all competing in a warm, productive marine environment. Coral reefs, yes, actual coral reefs, grew along portions of the Mediterranean coastline where conditions were right. These weren't as extensive as modern Caribbean or Pacific reefs, but they were there, building structures that would eventually fossilize, creating records we can study today. But the really interesting stuff was happening along the coasts. Because the Mediterranean wasn't surrounded by ocean, it was surrounded by land, and that land was unlike anything you'd see around the Mediterranean today. The northern shores, what we now call southern Europe, were covered in forests. Not the scrubby Mediterranean vegetation of modern times, but actual forests. Dense subtropical woodlands full of trees that have since gone extinct or migrated to warmer climates. Palms grew in southern Spain. Fig trees were common. Vegetation that today you'd associate with North Africa or the Middle East thrived across southern Europe. Why? Because the climate was different. The late Miocene was warmer than today, several degrees warmer on average. There was no permanent ice at the poles yet. Sea levels were higher, weather patterns were different. The Mediterranean region enjoyed what paleoclimatologists call a subtropical to warm temperate climate. Hot, humid summers, mild winters, plenty of rainfall along the northern coasts. And where you have lush vegetation, you get animals. Lots of animals. The shores of the pre-crisis Mediterranean were populated by creatures that would seem bizarre today. Ancestral elephants, not the massive woolly mammoths that would come later during the ice ages, but smaller, more primitive species that browsed the forests. Ancient horses, not much bigger than ponies, ran in herds across coastal plains. Rhinos, yes, rhinoceroses in Europe, multiple species of them, wallowed in rivers and browsed on low vegetation. Predators followed the prey. Saber-toothed cats, massive creatures with those characteristic elongated canines, hunted the forests and grasslands. Early hyenas, more diverse than modern species, filled scavenging niches. Ancient bear dogs, creatures that were kind of both and kind of neither, competed for food in the forests. This was the Mediterranean ecosystem 5.6 million years ago. A thriving, interconnected web of marine and terrestrial life, all depending on one critical fact. The connection to the Atlantic remained open, but that connection, that narrow strait at Gibraltar, it was more fragile than anyone living then could have understood. Not that anyone was living then. Not humans, anyway. We wouldn't evolve for another several million years, but if someone had been there to analyse the situation, they would have noticed something concerning about Gibraltar. The strait sat right on a tectonic boundary. The African plate pushing northward, the Eurasian plate resisting, and caught between them the Iberian microplate, a small crustal fragment that included modern Spain and Portugal. These three pieces of Earth's crust were grinding against each other in slow motion, creating complex geology that's difficult to map even today. The seafloor at Gibraltar wasn't stable, it was tectonically active, meaning it could rise or fall depending on the forces acting on it. Undersea volcanoes dotted the region, building structures that could potentially block the strait. Sediments washed down from the surrounding lands, accumulating on the seafloor, slowly building up the bottom of the channel. Most critically, the African and Eurasian plates were converging. Not quickly, maybe a centimetre or two per year, but enough that over geological time the strait was narrowing. The distance between Africa and Europe was shrinking. The channel connecting Mediterranean and Atlantic was getting smaller. For millions of years this hadn't mattered. The strait was wide enough that even slow narrowing didn't create problems. Water continued flowing freely between ocean and sea. But there's a threshold effect with these kinds of systems. You can narrow a channel for a long time with minimal consequences, then suddenly you cross a critical point where the flow can't keep up with demand. The Mediterranean was approaching that threshold. The exact mechanisms are still debated by geologists. There are multiple theories about what finally sealed Gibraltar, but the basic situation was becoming unstable. Too many geological forces pushing in the same direction. Continental collision narrowing the strait. Tectonic uplift raising the seafloor. Sediment accumulation building barriers. Possibly climate changes affecting sea levels. Individually, none of these factors would have been enough, but together they created a perfect storm of geological circumstances. And the Mediterranean's connection to the Atlantic, that lifeline that kept the sea alive, was about to be severed. The marine life in the Mediterranean had no idea what was coming. The whales continued their migrations following productive currents that had existed for millennia. The fish spawned in coastal shallows, their populations supported by nutrients flowing in from the Atlantic. The sharks hunted, the dolphins played, The coral polyps built their reefs one tiny skeleton at a time. On land, the animals followed ancient trails between feeding grounds and water sources. Herds moved with the seasons. Predators tracked their prey. Seeds sprouted, grew into trees, dropped seeds of their own. The whole magnificent ecosystem hummed along, seemingly eternal, seemingly secure. But geological processes don't care about ecosystems. They don't pause to consider the consequences of continental drift or tectonic uplift. They simply happen, driven by forces deep in the Earth's interior. Heat from radioactive decay, convection currents in the mantle, the slow, inexorable movement of crustal plates responding to pressures that had been building for millions of years. The Mediterranean was living on borrowed time. Every year the Strait at Gibraltar got a little narrower. Every century the flow of Atlantic water decreased by some tiny amount. The changes were too gradual to notice in any single lifetime, too slow to trigger alarm in any species adapted to stable conditions. But the threshold was approaching, and when it finally came, when the geological balance finally tipped and the Mediterranean lost its connection to the Atlantic, everything would change. The thriving sea would begin to die. The diverse ecosystems would collapse. The coastlines would retreat as water levels dropped. The Mediterranean, ancient remnant of the great Tethys Sea, warm and productive and full of life, was about to become something else entirely. Something that would seem impossible if we didn't have the geological evidence proving it really happened. A desert. A salt-crusted, sun-baked, lifeless desert, sitting 2 or 3 kilometers below sea level, the largest dry basin on Earth, stretching from Spain to the Middle East. But we're getting ahead of ourselves. Before we can understand the crisis, we need to understand what failed. And what failed was that narrow strait, that critical connection, that geological lifeline at Gibraltar. The clock was ticking. The Mediterranean's days as a living sea were numbered. So we've established what the Mediterranean was before everything went wrong. A thriving sea, warm and clear, teeming with life that had evolved over millions of years, creatures perfectly adapted to stable conditions, complex food webs, ecosystems in balance. Now let's talk about what destroyed it all. 5. 96 million years ago, something changed. Not suddenly, not catastrophically at first, but inexorably. The African tectonic plate, which had been drifting northward for millions of years, finally made full contact with the European plate at a very specific, very unfortunate location, the Strait of Gibraltar. Now you need to understand what the Strait of Gibraltar represented. It wasn't just a connection between the Mediterranean and the Atlantic, it was the only connection. The Mediterranean is basically a giant bowl surrounded by land on all sides except for this one narrow passage. Cut off that passage, and you've isolated an entire ocean from the global water system. And that's exactly what happened. The tectonic collision pushed up land at Gibraltar, creating a barrier where open water had existed before. The process probably took thousands of years, not a sudden closure, but a gradual rising of the seafloor, a slow constriction of the channel. First, the deepest parts of the strait became impassable, then the shallower sections. Then finally, maybe during one particularly strong tectonic spasm, the last connection closed completely. The Mediterranean was sealed off, landlocked, cut off from the Atlantic Ocean that had fed it for millions of years. At first, nothing seemed to change. The Mediterranean was enormous, containing enough water to cover the entire United States to a depth of about 3,000 feet. One sea. That much water doesn't just disappear overnight. But here's the thing about the Mediterranean that made this closure so catastrophic. It's located in a hot, dry climate zone. The sun beats down on it relentlessly. Evaporation rates are massive. Even today, with the Strait open and Atlantic water flowing in constantly, the Mediterranean loses more water to evaporation than it gains from rivers. Do the math on that. More water evaporating out than coming in. Under normal circumstances, this wouldn't matter because the Atlantic constantly replenishes what's lost. But now there was no Atlantic inflow, just rivers emptying into the basin. The Nile, the Rhone, the Po, dozens of smaller rivers bringing fresh water from surrounding lands. It wasn't nearly enough, not even close. The Mediterranean was losing water through evaporation about 3 times faster than rivers could replace it. 3 times faster, which meant that every year the sea level dropped. Not by much at first, maybe a few feet annually, but consistently, relentlessly, year after year after year. Imagine watching this happen over a human lifetime. You're born on the Mediterranean coast. As a child, you play on beaches where the water laps at your feet. By the time you're middle-aged, those same beaches are a mile inland, separated from the receding water by vast expanses of mud and salt. By the time you're old, the sea has dropped so far that from your childhood beach you can't even see the water anymore. It's over the horizon, dozens of miles away, hundreds of feet below where it used to be. And this process didn't stop with one lifetime. It continued for thousands of years, the sea level dropping and dropping and dropping, exposing seafloor that hadn't seen sunlight since the Mediterranean first formed. Ancient underwater mountains became islands, then towering peaks. Underwater canyons became dry gorges thousands of feet deep. The entire geography of the basin transformed as water drained away. But the water wasn't really draining anywhere. It was just evaporating, turning to vapor and drifting away on Mediterranean winds. And when water evaporates, it leaves behind everything that was dissolved in it. Salt. Massive quantities of salt. Seawater is about 3% salt by weight. Doesn't sound like much, but the Mediterranean contained roughly 3.7 million cubic kilometers of water. Do the calculation on how much salt that represents, and you get numbers that strain comprehension. Billions upon billions of tons of dissolved minerals. As the water evaporated away, all that salt had to go somewhere. It precipitated out, crystallized on the seafloor, accumulated in layers that grew thicker every year. First, the most common minerals crystallized out. Calcium carbonate, calcium sulfate, forming white deposits across the basin floor. Then, as the remaining water became more concentrated, more saturated with dissolved minerals, the pure halite began to form. Table salt, massive crystalline structures growing from the superheated brine. Think about what was happening here. As the sea level dropped, the remaining water became more and more saline, more concentrated. Today's ocean water is about 35 parts per thousand salt, but in the evaporating Mediterranean, the salinity kept climbing. 50 parts per thousand, 100, 200. Eventually reaching concentrations that would make the Dead Sea look fresh by comparison. Marine life didn't stand a chance. Species that had evolved in normal seawater conditions suddenly found themselves in brine. First, the most sensitive species died off. Fish, marine mammals, anything that needed stable salinity. Then the more resilient creatures, mollusks, crustaceans, organisms that could tolerate some variation. Finally, even the extremophils, the bacteria and archaea that could survive in harsh conditions, found their limits. When salinity reaches certain levels, when temperatures climb high enough, even the toughest life forms can't survive. The Mediterranean was dying, but it was just dying slowly, ecosystem by ecosystem, species by species. The shallow coastal areas went first as they were exposed to air and became dry land. Coral reefs that had taken millions of years to grow died and crumbled as the water dropped below them. Deep-sea vents that had supported unique ecosystems found themselves in increasingly saline conditions until even the specialized vent fauna couldn't survive, and all the while the salt kept accumulating. In some parts of the Mediterranean basin, salt deposits grew to staggering thicknesses, not just a few feet, not even hundreds of feet. In places, the salt accumulated to depths of 2,000 to 3,000 meters. That's nearly 2 miles of solid salt. Layer upon layer upon layer, each representing years or decades of evaporation, slowly burying the ancient seafloor under a blanket of crystalline minerals. Picture what this landscape looked like. The former seafloor, now exposed to air, stretched out as a vast salt desert. White plains of crystalline minerals reflecting sunlight with blinding intensity. In the deepest parts of the basin, now 3 to 5 kilometers below global sea level, the environment would have been absolutely hellish. The air pressure at those depths would have been about 5 times normal atmospheric pressure. Temperatures during summer would have soared to levels rarely seen on Earth's surface. Some estimates suggest temperatures of 50 to 60 degrees Celsius, maybe even hotter in the deepest depressions. And it wasn't all dry salt flats. In the lowest areas, where rivers still managed to flow down the tremendous elevations, hypersaline lakes formed. Lakes so salty that nothing could live in them except perhaps a few extremophile bacteria. Lakes that might have been bright pink or red from the few microorganisms that could tolerate such conditions. Lakes that would have been surrounded by vast deposits of white salt, creating landscapes that would have seemed utterly alien. The rivers themselves faced a completely transformed situation. Rivers like the Nile, which today flows gently into the Mediterranean at sea level, suddenly found themselves perched on cliffs thousands of feet high. They didn't just flow into the basin. They plummeted down massive waterfalls, carving deep canyons through exposed rock as they dropped to the basin floor far below. The Rhone, the Po, the Ebro, all of them cutting enormous gorges as they adapted to the new reality of a Mediterranean that had dropped kilometers below its former level. Some of these ancient river canyons still exist, buried now under sediment and water. The Nile carved a canyon that extended all the way to Aswan, hundreds of miles inland, cutting thousands of feet down into bedrock. When the Mediterranean finally refilled, these canyons were drowned and slowly filled with sediment, but geologists can still detect them through seismic surveys and drilling. They're ghosts of the Messinian Crisis, evidence of how dramatically the landscape transformed. But here's what makes this story even more remarkable. This wasn't a brief event. This wasn't a crisis that lasted a few years or a few decades. The Messinian Salinity Crisis lasted for approximately 640,000 years. 640,000 years. Let that number sink in. All of recorded human history, everything from the first cities to modern civilization, spans maybe 10,000 years. The Messinian Crisis was 64 times longer than that. For over 500,000 years, the Mediterranean remained a salt desert. Generations upon generations of whatever animals lived around its edges would have known nothing but this landscape. No living creature would have carried memories of when this had been a sea. The Mediterranean as a thriving marine ecosystem would have been as forgotten as if it had never existed. During this incomprehensible stretch of time, the situation may have fluctuated somewhat. The climate wasn't static. Some periods might have been wetter, allowing more river inflow, perhaps even creating brief episodes where shallow seas reformed in the deepest parts of the basin. Other periods might have been even drier, causing even more extreme evaporation. There's evidence that the crisis occurred in multiple phases, not just a steady, continuous evaporation, but a complex series of desiccation events. The strait might have reopened briefly at times, allowing temporary inflows of Atlantic water before closing again. Each closure would restart the evaporation process. Each brief refilling would create new layers in the geological record. The salt deposits themselves show this complexity, with multiple distinct layers of different mineral compositions, each telling a story of different environmental conditions. But through it all, the fundamental situation remained the same. The Mediterranean was cut off from the global ocean system. It was evaporating faster than it could be replenished, and it remained a hostile, largely lifeless desert basin for over 600,000 years. Meanwhile, something else was happening. Something that would eventually end this crisis in the most dramatic way imaginable. At Gibraltar, where the African and European plates had closed the strait, the Atlantic Ocean pressed constantly against the barrier. Millions upon millions of tons of water pushing against rock, probing for weaknesses, finding cracks, exploiting any vulnerability. And the barrier wasn't uniform. It was made of rock pushed up by tectonic forces, sedimentary layers, some hard, some soft, limestone and sandstone and clay. Some sections were hundreds of meters thick, others might have been much thinner. The Atlantic didn't just press against one monolithic wall, it pressed against a complex geological structure with varying resistance to erosion. Ocean water is remarkably good at eroding rock, especially when it has time, and it had time. 640,000 years of time. During that entire period, Atlantic water was working on the Gibraltar barrier. During storms, waves would pound against it with tremendous force. Even during calm periods, the constant pressure, the endless chemical weathering, the slow dissolution of minerals, all of it contributed to weakening the barrier. You have to understand the pressure differential here. On one side of the barrier, the Atlantic Ocean at normal sea level. On the other side, the Mediterranean basin, now 3 to 5 kilometers below normal sea level. That's a height difference comparable to some of Earth's tallest mountains. The gravitational potential energy represented by that difference was staggering. If the barrier failed, water wouldn't just flow from the Atlantic into the Mediterranean, it would fall thousands of feet, and the longer the crisis lasted, the worse the situation got. Every year that the Mediterranean remained cut off, more water evaporated. The basin floor dropped lower. The pressure differential increased. The potential energy grew. The Atlantic pressed harder against the barrier, found more cracks, exploited more weaknesses. It was only a matter of time, not if the barrier would fail, but when. And what would happen when millions of years of geological pressure released all at once. The stage was set for one of the most catastrophic events in Earth's history. A planet-changing flood that would reshape continents and alter global climate. But before that flood could happen, something had to give way. Some critical weakness in the Gibraltar barrier had to finally fail under the relentless pressure of an ocean that had been waiting 640,000 years to break through. That moment was coming, and when it arrived, the Mediterranean would transform from desert to ocean in less time than it takes for most geological processes to even begin. But we're getting ahead of ourselves. First, we need to understand exactly what happened when the barrier finally failed. Because what happened next didn't just change the Mediterranean, it changed the entire planet. Picture this, it's 33 million years ago. On one side of a narrow rock barrier stands the Atlantic Ocean, waves crashing against cliffs, water level exactly where it's supposed to be. On the other side, 4 kilometers below, stretches the most hostile landscape on Earth, the Mediterranean desert, a scorched hellscape of salt and rock where nothing lives, where temperatures reach levels that would kill anything foolish enough to wander there, and between them, a threshold of rock. That's it. Just limestone and compressed sediment holding back the entire Atlantic Ocean from flooding into a basin nearly as large as India. But here's the thing about geological barriers. They don't last forever, especially when you've got 100 meters of water pressure pushing against one side and nothing but air pushing back from the other. That's roughly 10 atmospheres of pressure difference, about the same pressure differential you'd experience if you dove 100 meters underwater. Except this pressure isn't being experienced by your body. It's being experienced by every square meter of rock at the Gibraltar threshold. Millions of tons of force, constant and unrelenting every second of every day for hundreds of thousands of years. Think about what that means. Water finds weakness. It always does. Every tiny crack in the rock, every fault line, every place where harder stone meets softer sediment. The Atlantic is probing these weaknesses, testing them, exploiting them. Saltwater seeps into microscopic fissures. It freezes and expands during cold periods. It dissolves soluble minerals. It carries abrasive sediment that grinds away at stone. Year after year, century after century, the barrier is weakening. And it's not just erosion doing the work. The entire region is tectonically active. The African plate is grinding northward against the Eurasian plate, the same tectonic forces that created the Mediterranean basin in the first place. This creates stress, earthquakes, the ground literally shaking and fracturing. Every tremor widens existing cracks. Every major quake can shift entire rock formations. The Gibraltar threshold isn't a solid wall. It's a stressed, fractured, eroding barrier that's been holding back an ocean for over 500,000 years. Something has to give. But when? That's the question that would have haunted any geologist observing the situation. If geologists had existed 33 million years ago, they would have been frantically calculating failure probabilities, measuring stress points, trying to predict when the catastrophe would occur. Because it wasn't a question of if, it was only ever a question of when. The actual trigger might have been an earthquake. The region experiences them regularly, even today. The Gibraltar Arc is seismically active. A magnitude 6 or 7 earthquake could easily fracture weakened rock formations. Or maybe it was simpler than that. Maybe it was just erosion, water slowly wearing away at a critical support structure until one day, one specific day, 33 million years ago, a crucial section of rock simply dissolved or collapsed or crumbled away. Sometimes the most dramatic events in Earth's history don't have dramatic causes. Sometimes they're just the culmination of millions of tiny incremental changes that finally cross a threshold. Like the last grain of sand that triggers an avalanche. Nobody could point to that grain and say this is the one that caused it, but without it the avalanche wouldn't have happened. What we know is this. Approximately 33 million years ago, the Gibraltar threshold failed. The first breach was probably small, maybe just a trickle, a stream of Atlantic water finding a path through fractured rock, tumbling down into the Mediterranean basin. At first, it might have been no more impressive than a large river. water cascading over rocks, creating a waterfall that dropped 4 kilometers into the desert below. If you could have stood there at that moment, if you could have witnessed the very beginning of the Zanclean Flood, you might have thought it looks manageable, significant, but not world-changing. You would have been catastrophically wrong. Because here's what happens when water starts flowing through a breach in a geological barrier. It doesn't just flow, it erodes. Every cubic meter of water carries kinetic energy. When that water hits rock, it transfers that energy. It scours, it grinds, it carries abrasive sediment that acts like liquid sandpaper. And the faster the water flows, the more erosive power it has. This creates what engineers call a positive feedback loop. A little bit of water flows through the breach. That water erodes the channel, making it slightly larger. More water flows through the larger channel, which erodes it even faster, which allows even more water to flow through, which erodes even more, on, exponentially accelerating. Within hours, that initial trickle became a torrent. Within days, it was a cataract beyond anything the modern world has ever seen. Within weeks, the breach had widened from meters to hundreds of meters, and the process was accelerating. The hydraulic forces involved are almost impossible to comprehend. Modern engineering gives us some reference points. The largest waterfalls on Earth today, Victoria Falls, Niagara Falls, impressive as they are, they drop tens of meters, maybe 100 meters at most. The Zanclean Flood was dropping water 4 kilometers, 40 times higher than the tallest waterfalls on Earth. The water hitting the bottom of that fall would have been moving at terminal velocity, hundreds of kilometers per hour, carrying enough kinetic energy to pulverize rock, to excavate enormous canyons in days or weeks instead of millennia. And it wasn't just the vertical drop creating erosion. The sheer volume of water was unlike anything in Earth's history. As the breach widened, more and more of the Atlantic's flow was diverted through Gibraltar. First, it might have been equivalent to the Amazon River, the largest river on Earth, already an almost unimaginable volume of water. But that was just the beginning. The breach kept widening. The physics of fluid dynamics meant that as the channel enlarged, water velocity didn't decrease proportionally. The pressure differential was so enormous, over 100 meters of head pressure, that water just kept accelerating through the gap. Within months, the flow might have exceeded the combined discharge of every river on Earth. All of that water, millions of cubic meters per second, focused through a single channel at Gibraltar. The sound alone would have been apocalyptic. Modern large waterfalls can be heard for kilometers. The Victoria Falls, locals call it Mosioatunya, the smoke that thunders. The roar is audible 40 kilometers away. The Zanclean Flood would have been thousands of times larger. The acoustic energy would have been beyond anything in human experience. If humans had existed then, if they could have somehow survived near enough to hear it, the sound would have been constant, overwhelming, vibrating through the ground, through the air, through your bones. A physical presence, not just a noise. The kind of sound that makes you understand, deep in your primate brain, that you are witnessing forces that make human existence irrelevant. And the visual? Imagine standing on what remained of the Gibraltar threshold looking down. Below you, a vertical drop of 4 kilometers. That's the height of the world's tallest mountains. You'd be looking down through clouds. The mist and spray from the waterfall would create permanent cloud systems, weather patterns generated by the sheer volume of evaporating water. Through gaps in the clouds, you might catch glimpses of the bottom, of water hitting the desert floor with such force that it's creating craters excavating canyons, carrying away millions of tons of salt and sediment, of rivers of water kilometers wide spreading out across the Mediterranean basin, filling depressions, creating temporary seas that grow larger every day, of a landscape transforming in real time. What was desert yesterday is a shallow sea today. What was a shallow sea last week is now hundreds of meters deep. But back at the threshold, the real drama is the breach itself. It's still widening. The initial crack that started all this, that first small channel through weakened rock, it's now a canyon, kilometers wide and growing. The Atlantic isn't just leaking into the Mediterranean anymore, it's excavating the Gibraltar Strait, creating in just months or years a geological feature that looks like it should have taken millions of years to form. The erosion is selective but devastating. Softer rock formations are obliterated, carried away as sediment in the monstrous current. Harder formations, resistant limestone and compressed conglomerates, they survive longer, creating temporary barriers and shelves. But they're being undermined, eroded from below, attacked by hydraulic forces that would make modern engineering catastrophes look like minor inconveniences. When one of these harder formations finally fails, it doesn't erode gradually. It collapses catastrophically. Thousands of tons of rock suddenly giving way, creating temporary dams that back up the flow before being overwhelmed and swept away. Each collapse sends shock waves through the water, tsunamis racing down the growing channel, walls of water hundreds of meters high, carrying boulders the size of houses, slamming into whatever obstacles remain in their path. The geology of the region is literally being rewritten. Fault lines that were stable for millions of years are suddenly under completely different stress patterns. The enormous weight of water being removed from the Atlantic basin, the enormous weight being added to the Mediterranean basin. These are changing how the tectonic plates interact. Earthquakes that would have been significant under normal circumstances are now triggering secondary collapses, widening the breach even faster. This is runaway geological catastrophe. Every effect creates new causes. Every change accelerates the next change. There's no equilibrium, no balance, just exponential escalation toward an endpoint that was inevitable from the moment the first trickle breached the threshold. By the time the breach reached its maximum width, and that probably took just a few years, maybe a decade at most, the Gibraltar Strait had become something that had never existed before and would never exist again. A channel kilometers wide, carrying water flows that defied comprehension. Conservative estimates suggest the peak flow might have reached 100 million cubic meters per second. That's 1,000 times the flow of the Amazon. That's more water than all the rivers on Earth combined, times 10. For reference, Niagara Falls, one of the most powerful waterfalls in the modern world, carries about 2,800 cubic meters per second. The Zanclean Flood, at its peak, was carrying 35,000 times more water than Niagara Falls, and it was dropping that water 40 times farther. The kinetic energy being released every second exceeded the output of thousands of nuclear power plants. If you could somehow harness even a fraction of that power, you could supply electricity to every city on modern Earth with energy left over. But you can't harness it. You can only witness it and try to comprehend forces that make human engineering achievements look like children playing with toys. This was Earth operating at a scale that reminds us how temporary and fragile our surface modifications really are. How quickly natural processes can reshape landscapes we think of as permanent. The Mediterranean desert, that hellscape that had existed for over 600,000 years, was being erased. not gradually over geological time, but in real time. Fast enough that if you were watching, you could see the changes day by day, hour by hour, and there was no stopping it. No way to plug the breach, no way to slow the flow. The Atlantic was going to equalize with the Mediterranean basin. Physics demanded it. The only question was how long it would take. As the Mediterranean filled, the water level rose and the pressure differential decreased. This should have slowed the flow, but the erosion had already done its work. The Gibraltar Strait had been excavated to depths that would allow massive water flow even with reduced pressure. The process had taken on a momentum that would carry it through to completion. The barrier that had held for over 500,000 years was gone. In its place was a channel that would become one of the most important geographical features on Earth. Permanent connection between the Atlantic and the Mediterranean that would shape human history, enable civilizations, and create the strategic waterway that nations would fight over for thousands of years. But that was all in the distant future. For now there was only water. More water than had moved through any single place in Earth's history. Water erasing a desert and creating a sea. Water reshaping the planet in the most dramatic geological event of the last 10 million years. The breaking point had been reached, the barrier had failed, and now came the deluge. Because here's the thing about that initial breach at Gibraltar. It didn't stay small. Water doesn't work that way. Once it starts flowing, it erodes, it carves, it destroys everything in its path with relentless, patient fury. And what started as a trickle through a weak point in the land bridge became something that defies human comprehension. Within days, maybe hours, the breach widened. The Atlantic, pressed against that barrier for hundreds of thousands of years, found its opening and exploded through with force that nothing on Earth could stop. The rock at Gibraltar, weakened by millennia of weathering and the constant assault of Atlantic waves, crumbled under the pressure. What had been a narrow gap became a torrent, then a deluge, then something so massive that modern science struggles to find words adequate to describe it. The best estimates, based on the geological evidence carved into the bedrock beneath modern Gibraltar, suggest that at its peak, approximately 100 million cubic meters of water per second was pouring through that gap. Let that number sink in for a moment. 100 million cubic meters, every single second. Imagine trying to visualize that volume. You can't. The human brain isn't equipped to process numbers that large in any meaningful way. But here's a comparison that might help. The Amazon River, the largest river on Earth by volume, carries about 209,000 cubic meters of water per second at its mouth. That's enormous. The Amazon drains nearly 40% of South America. It's so massive that it dumps enough fresh water into the Atlantic to create a visible plume of brown river water, extending hundreds of kilometers into the ocean. The Zanclean Flood, at its peak, was flowing at roughly 1,000 times the Amazon's volume, all concentrated in one place, all thundering through a gap that was initially just a few kilometers wide. Try to picture that. Take the Amazon River, already so vast it looks like an ocean, multiply its flow by 1,000, and force all of that water through a channel narrower than the width of a modern city. The result wouldn't just be a waterfall, it would be a weapon of planetary-scale destruction. Think of it like this. You take a garden hose and attach one of those high-pressure nozzles. The pressure builds, the water accelerates, and it shoots out with enough force to strip paint off wood. Now, imagine that same principle, but instead of a garden hose, you're using 90% of all the water flow on Earth's surface, because that's effectively what was happening. During the peak of the flood, Essentially, all of Earth's hydrological cycle was being temporarily redirected through Gibraltar. Rivers around the world were feeding into oceans that were feeding into the Atlantic, that was pouring into the Mediterranean basin at a rate that makes modern waterfalls look like decorative fountains. The physical structure of what formed at Gibraltar would have been unlike anything else in Earth's history. Because the Mediterranean basin floor wasn't at sea level, it was between 1 and 3 kilometres below it. That depth variation depended on location. The western Mediterranean near Spain was relatively shallow, maybe 1,000 metres below sea level. But the eastern basin, near modern-day Greece and Libya, had dried to depths of 3 kilometres or more below the Atlantic surface. This created a waterfall. Not a waterfall like Niagara Falls or Victoria Falls, impressive as those are. A waterfall taller than 3 of the world's tallest buildings stacked on top of each other. A waterfall carrying 1,000 times the Amazon's flow. A waterfall whose roar would have been audible for hundreds, possibly thousands of kilometres in every direction. Try to imagine standing on the African coast, say in what's now Morocco, 500 kilometres from Gibraltar. You're far enough away that you can't see the strait. There are mountains and valleys between you and the coast, but you can hear it. A constant thunderous roar that never stops, day or night. It sounds like the sky is tearing apart. It sounds like the earth is splitting open. It's so loud that it overwhelms every other sound. Birds don't sing. Animals don't call. There's just the endless, overwhelming thunder of 100 million cubic meters of water per second, falling 3 kilometers and hitting the basin floor with the force of a continuous planetary bombardment. The mist alone would have been apocalyptic. When that much water falls that far, it doesn't just create spray, it creates weather systems. The impact of all that water hitting the basin floor would have vaporized enormous quantities of it. The heat generated by the kinetic energy conversion would have been astronomical. Water falling 3 kilometers accelerates to terminal velocity. When it hits the bottom, all that kinetic energy has to go somewhere. It converts to heat, to sound, to the pulverization of rock, and to the generation of massive amounts of water vapor. That vapor, rising from the impact zone, would have created permanent storm systems around the cataract. Massive convection columns of moisture-laden air rising into the atmosphere, cooling, condensing, and falling back as torrential rain. The entire region around Gibraltar would have been perpetually shrouded in clouds and rain so thick that visibility would have been measured in meters, not kilometers. The sun wouldn't have been visible. The stars would have been impossible to see. Just endless grey clouds, endless rain, and the eternal thunder of the falls, and the rainbows. When sunlight did occasionally break through the clouds and mist, the rainbows would have been spectacular beyond description. Full 360-degree circular rainbows surrounding the entire cataract. Double rainbows, triple rainbows, the entire electromagnetic spectrum being refracted through billions of water droplets suspended in the air. It would have been beautiful and terrifying in equal measure. Nature's fury creating nature's most peaceful symbol on an impossible scale. But the most incredible thing wasn't happening at Gibraltar, it was happening across the basin floor. Because all that water pouring through the strait had to go somewhere. It wasn't disappearing, it was filling the basin from the bottom up, and it was filling it fast. Picture the Mediterranean basin 33 million years ago. Thousands upon thousands of square kilometres of salt flats, dried lakes, ancient river channels carved deep into the bedrock. Some areas are relatively flat. Others are deeply eroded badlands, canyons, gorges created by 500,000 years of wind and the occasional violent flash flood. And now, from the western edge of this desert, a wall of water is advancing, not a wave like a tsunami, which is tall but passes quickly. This was a permanent wall, an advancing front of water that never stopped, never receded, just kept coming day after day, week after week, month after month. The speed of advance varied depending on the topography. In flat areas, where the basin floor was relatively level, the water might have spread quickly, advancing tens of kilometers per day. Imagine watching that. You're standing on a salt flat that extends to the horizon in every direction. Then in the distance you see something strange, a line across the landscape. As you watch, it grows. Within hours you realize it's water. Within a day, it's kilometers closer. Within a week, it's covered everything you can see. But in other areas, especially in the deeply eroded sections of the basin, the advance would have been even more dramatic. Water, pouring into ancient canyons and valleys, would have created temporary rivers of unimaginable power. These weren't rivers in any normal sense. They were more like sustained flash floods, carrying not just water, but everything the Atlantic had picked up at Gibraltar and transported across the basin. Rock fragments, boulders, sediment, all churning together in a turbulent flow that scoured the basin floor clean. The erosive power of the flood would have been concentrated in these channels. Water moving at high speed, under tremendous pressure, carrying abrasive sediments, can cut through solid rock like a saw. And that's exactly what happened. The geological record shows massive erosion channels carved into the bedrock during the Zanclean Flood. Some of these channels are hundreds of meters deep and tens of kilometers long. They were carved not over millions of years, but over months or years by the sustained fury of water, moving faster and carrying more sediment than anything in modern experience. This sediment transport alone defies easy comprehension. When water moves that fast and carries that much volume, it can transport enormous particles. Boulders the size of cars, fragments of rock weighing hundreds of tons, all being carried along in the turbulent flow like leaves in a stream. Geological studies of the Mediterranean seafloor show deposits from this period containing rock fragments that should only have been transported by extraordinary flows. These aren't pebbles or sand. These are massive chunks of bedrock that were ripped from the Gibraltar Channel, transported hundreds of kilometers across the basin, and deposited wherever the flow velocity finally dropped enough for them to settle. The noise wouldn't have been limited to Gibraltar either. All across the advancing waterfront there would have been a continuous roar. The sound of water rushing through channels, the crack of ice and salt formations being destroyed by the advancing flood, the grinding of rocks being transported along the basin floor. If any animals had managed to survive in the Messinian desert by finding isolated water sources, they would have heard the flood coming long before they saw it, that constant roar growing louder day by day until finally the water arrived and either trapped them or forced them to flee to higher ground. And think about the temperature effects. The Atlantic Ocean wasn't frozen, but it was relatively cold, especially at depth. The Mediterranean basin, meanwhile, had spent hundreds of thousands of years as a desert, baking under the Mediterranean sun. Surface temperatures in summer could have exceeded 50 degrees or more. Now you're pouring millions upon millions of cubic meters of cold Atlantic water into this superheated basin. The temperature differential would have created its own weather systems. Massive evaporation from the heated basin floor meeting cold water, convection currents strong enough to generate perpetual storms. The entire basin would have become a cauldron of atmospheric chaos. But perhaps the most mind-bending aspect of the deluge was what was happening back at Gibraltar. Because the erosive power of the flood wasn't just affecting the basin floor, it was also carving the Gibraltar Channel itself deeper and wider. Every second that water poured through that gap, it was removing more rock. The channel that had started as a relatively narrow breach was being systematically destroyed by the very water flowing through it. This created a feedback loop. Wider channel means more water flow. More water flow means more erosive power. More erosive power means even wider channel. The process was self-reinforcing, self-accelerating, unstoppable. Geological evidence suggests that the Gibraltar Channel was carved to depths of 200 meters or more below its original breach point. That's not weathering. That's not normal erosion. That's catastrophic scouring by the most powerful water flow in Earth's history. The rock removed from Gibraltar had to go somewhere. It was being transported into the basin, adding to the chaos of sediment and debris being churned through the floodwaters. Some of this material settled relatively close to the strait, creating massive underwater debris fans. Other material was carried hundreds of kilometers before finally being deposited. Today, geologists can identify these deposits in core samples taken from the Mediterranean seafloor. They're called the Zanclean Flood deposits, distinct layers of sediment containing rock fragments that could only have come from Gibraltar, transported and deposited during a catastrophically short period. And remember, this wasn't a one-time event. This was continuous. Day after day after day, 100 million cubic meters per second pouring through Gibraltar. The waterfall never stopped. The erosion never ceased. The advance of water across the basin floor never paused. It was relentless, inevitable, one of the most powerful geological processes ever to occur on Earth's surface. A planet-scale demonstration of what happens when water, given enough time and pressure, decides to go somewhere. Nothing could stop it. Nothing could slow it. It simply was, a force of nature so vast that it temporarily rewrote the rules of Earth's hydrological cycle. Human language struggles to capture events at this scale. We can calculate the numbers, map the geological evidence, trace the sediment deposits. But actually comprehending what it would have been like, that's beyond our capacity. We're a species that evolved in relatively stable environments. Our ancestors experienced floods, storms, natural disasters. But nothing, absolutely nothing in human experience prepares us for understanding a flood that channeled 90% of Earth's water through a single gap, created the largest waterfall in planetary history, and reshaped an entire ocean basin in less time than it takes for a human generation to pass. But the numbers don't lie. The geology doesn't lie, and both tell the same incredible story. For a brief moment in Earth's history, the entire Mediterranean became a demonstration of water's unstoppable power. A demonstration that would reshape the climate, geography, and ecology of an entire region. And it was just getting started, so the water is flowing. The Gibraltar Strait has failed, and millions of cubic meters of Atlantic seawater are pouring through every single second. The Mediterranean basin, empty for over 600,000 years, is starting to fill. But here's where things get really interesting. How long did it actually take to fill an ocean? The simple answer is we don't know exactly. The complicated answer is it depends who you ask and which evidence you trust. Some geologists think it took just a few months. Others argue for several thousand years. The most widely accepted estimate, based on multiple lines of evidence, sits right in the middle at about 2 years. 2 years to fill a basin containing over 7 million cubic kilometers of water. Think about that for a second. The Mediterranean basin is roughly 3,000 kilometers long and 1,500 kilometers wide at its greatest extent. At its deepest point, it would need to be filled to over 5,000 meters, and according to the leading estimates, nature accomplished this in just 730 days. That's not filling. That's drowning the landscape at a speed that defies comprehension, but not everyone agrees with the 2-year timeline. Some models suggest the refilling could have taken anywhere from 3 months to 10,000 years. The debate centers on one critical question: how fast could water actually flow through the Gibraltar Strait? If the initial breach was small, maybe just a few hundred meters wide, the filling would have been relatively gradual. Thousands of years of steadily rising water levels as the channel slowly widened through erosion. But if the breach was catastrophic, if the entire Gibraltar barrier failed at once, creating a channel that rapidly expanded to tens of kilometers wide, then the filling would have been apocalyptically fast. The geological evidence suggests catastrophic. The sediment layers at Gibraltar show massive erosion channels carved hundreds of meters deep into bedrock. The kind of erosion that doesn't happen gradually, the kind that requires water moving at speeds that would tear solid rock apart. Computer models of this scenario consistently arrive at that 2-year estimate. Give or take a few months depending on the variables you adjust. Let's go with that timeline. 2 years, 730 days of the most dramatic geological transformation in Mediterranean history. Picture what that actually meant on the ground. The first areas to flood would have been the deepest parts of the basin, the abyssal plains that had been dry salt flats for over 500,000 years. These were vast expanses of crystallized evaporites, some layers hundreds of meters thick, salt, gypsum, halite, all the minerals that had precipitated out as the Mediterranean evaporated. When the Atlantic water hit these salt flats, something remarkable happened. The water didn't just flow over them, it dissolved them. Salt is incredibly soluble. A cubic meter of water can dissolve hundreds of kilograms of salt. So as the flood advanced, it was literally eating the landscape, converting solid ground into super-concentrated brine. This created something that doesn't exist in nature anymore, a layer of incredibly dense salty water at the bottom of the filling basin with fresher Atlantic water flowing on top. The advancing waterline would have been visible from hundreds of kilometers away, not as a distinct wave, but as a line of transformation moving across the landscape at speeds that varied depending on the local topography. In the deepest parts of the basin, where the floor was relatively flat, the water advanced fast, maybe several kilometers per day. But it wasn't a dramatic wall of water. It was more like watching a bathtub fill, except the bathtub was the size of a small continent. But here's where things got weird. The Mediterranean basin wasn't uniformly flat. It was a complex landscape of deep channels and raised plateaus, areas that had been uplifted by tectonic forces over the millennia, or regions where erosion had been less severe during the dry period. When the water reached these high points, it created something extraordinary: temporary islands. Imagine being on one of these elevated regions as the water approached. At first it would have been a distant glint on the horizon, a line of silver where there should only be white salt flats. Over days or weeks that line would grow closer. The air would change as moisture from the advancing sea began affecting local weather patterns. Rain would have fallen on regions that hadn't seen precipitation in hundreds of thousands of years. Then the water would arrive, not all at once, but as a gradually encroaching presence that transformed the landscape around you. What had been a continuous salt flat became a shrinking plateau, surrounded by an ever-expanding sea. Some of these temporary islands would have been enormous, plateaus the size of modern countries, elevated just a few hundred meters above the deepest parts of the basin. For months, maybe years, they would have remained above water even as the sea level continued rising. Each one would have been a refuge, a last piece of dry land in a landscape being consumed by the returning ocean. Eventually, though, the water won. One by one, these temporary islands disappeared beneath the waves. First the smallest outcrops, then the larger plateaus. Finally the highest points, succumbing as the sea level approached its final elevation. The weather during this period would have been absolutely insane. You're taking a region that had been hot, dry and stable for hundreds of thousands of years, and suddenly introducing a rapidly expanding body of water. Water that was evaporating at tremendous rates as it flowed from the cold Atlantic into the hot Mediterranean basin. The amount of moisture being pumped into the atmosphere would have been staggering. Millions of cubic meters of water vapor every day, creating weather systems that the region had never experienced. Massive thunderstorms would have formed along the advancing waterline, where hot air rising from the still dry salt flats met moisture-laden air from the new sea. Lightning would have been nearly constant. Not the occasional storm you see today, but continuous electrical discharges. Enormous temperature gradients drove atmospheric instability. The ancient coastlines around the Mediterranean would have experienced precipitation events unlike anything in the historical record. Flash floods from rainfall that would have seemed biblical in intensity. But the weather effects weren't just local. The Mediterranean was acting like a massive heat engine, taking cold Atlantic water and warming it dramatically as it spread across sun-baked salt flats. This created powerful updrafts that affected atmospheric circulation across southern Europe and North Africa. Some climate models suggest the refilling period caused temporary cooling in northern Europe as atmospheric patterns shifted. Conversely, North Africa might have experienced increased rainfall as moisture-laden air from the Mediterranean was pulled southward. The chemistry of the filling basin was equally dramatic. You had cold, relatively fresh Atlantic water with a salinity around 36 parts per thousand, mixing with super-concentrated brine that formed as the water dissolved salt deposits. In some areas, the bottom water might have reached salinities of 100 parts per thousand or higher. Density differences meant these water masses didn't mix easily. Instead, they formed distinct layers. The dense brine sank to the deepest parts of the basin, creating a stratified water column that would take thousands of years to fully mix. Temperature gradients were just as extreme. The Atlantic water entering through Gibraltar would have been relatively cold, maybe 15 to 20 degrees Celsius depending on the season. But as it flowed across the sun-heated basin, it would have warmed rapidly. The surface water in some areas might have reached 35 or 40 degrees Celsius, hot enough to be uncomfortable to touch. Combined with the salt concentration variations, this created a Mediterranean that was fundamentally different from anything we see today. A chemically and thermally stratified body of water in violent disequilibrium, slowly mixing and stabilizing over millennia. The sedimentary evidence for all this is written in the rocks. All around the Mediterranean basin, geologists have found layers that tell the story of the refilling. At the bottom you have the evaporites, the salt and gypsum that precipitated during the Messinian Salinity Crisis. These layers can be hundreds of meters thick in the deepest parts of the basin. They represent over 600,000 years of evaporation and mineral accumulation. Then, suddenly those evaporate layers end. The transition is remarkably sharp. In some locations, geologists have found the boundary between the last evaporate deposits and the first marine sediments compressed into a layer just a few centimeters thick. This represents the moment when the flood arrived, the end of the desert and the beginning of the sea. Above that boundary, you find something completely different: marine sediments, clay, silt, and sand deposited from suspension as the water flowed in and then settled. These sediments are often chaotic and poorly sorted, exactly what you'd expect from catastrophically fast deposition. In some locations there are massive gravel beds, boulder-sized rocks deposited by the incredible current velocities during the initial stages of flooding. But the most telling evidence comes from the thickness of these early marine sediments. If the refilling had taken thousands of years, you'd expect relatively thin, well-sorted sediment layers. Slow deposition allowing time for particles to settle based on size and density. Instead, what geologists find are thick, chaotic deposits laid down extremely rapidly. Some cores show over 10 meters of early flood sediments. That's not thousands of years of slow accumulation. That's months or years of violent, turbulent deposition. The sediments also contain evidence of the advancing waterline. In areas that were higher in elevation, the transition from evaporites to marine sediments happens later in the geological record. You can literally track the flood's progress by looking at when different locations show the change from dry land to underwater deposition. It's like watching a time-lapse video preserved in rock. Then there are the erosional features, the scour marks carved into the seafloor by the incoming water. In some locations, geologists have mapped channels carved hundreds of meters deep into the evaporate layers. These aren't rivers. They're the tracks left by underwater currents moving at speeds that would rival the fastest rivers on Earth today. The only way to create that kind of erosion is with truly catastrophic water velocities maintained over months or years. One of the most dramatic pieces of evidence comes from seismic surveys of the Mediterranean seafloor. These surveys use sound waves to image the layers of sediment and rock beneath the ocean floor. What they reveal is remarkable. The evaporate layers from the Messinian period aren't smooth and continuous. They're deeply eroded, carved into complex three-dimensional patterns by the returning water. Some areas show erosional channels stacked on top of each other, suggesting multiple stages of flooding as the water level rose and currents shifted. The rate of sea level rise during the refilling would have been truly staggering. If you accept the 2-year timeline and you know the Mediterranean needed to rise by an average of about 1,500 meters to reach its current level, the math becomes straightforward. That's over 2 meters per day on average. But averages don't tell the whole story. The filling wasn't constant. It varied based on the season, the Atlantic tides, and the evolving shape of the Gibraltar Channel. Some researchers think there were periods when sea level rose much faster, maybe 5 or even 10 meters per day in the early stages when the flow was most intense and the basin was deepest. Imagine standing on one of those temporary islands watching the waterline. In the morning the shore is 100 meters away. By evening it's advanced 10 meters closer. The next day, another 10 meters. You can literally see the island shrinking day by day, hour by hour. That's not a gradual geological process, that's something you could watch happen. Something that would have been terrifying if anything had been there to witness it. Of course, nothing was there to witness it, at least nothing we have evidence for. 5 million years ago, the Mediterranean region wasn't home to any large terrestrial animals that we know of. The basin had been too hostile for too long, but the Atlantic waters flowing in would have carried marine life, fish, plankton, bacteria, all swept along by the current and deposited in this strange new environment. Most of them probably died. The chemistry was all wrong. The temperature gradients were extreme. The water was too salty in some places, not salty enough in others. But some organisms survived. Some found niches in this chaotic new ecosystem and began reproducing. Over months and years, these pioneer species established populations. Then new species arrived, either swept in by subsequent currents or migrating along the seabed from the Atlantic. Slowly, ecosystem by ecosystem, the Mediterranean came back to life. But that was a process that took thousands or even millions of years. During the initial refilling, the Mediterranean wasn't a living sea. It was a chemical and physical experiment on a geological scale, a mixing chamber where ocean water met evaporate minerals and created something the planet hadn't seen before or since. The water that eventually filled the basin bore little resemblance to either the Atlantic source or the future Mediterranean. It was a transitional state, a brief geological moment preserved now only in sediment layers and chemical signatures. By the time 2 years had passed, the transformation was complete. The desert was gone. The salt flats were buried under thousands of meters of seawater. The temporary islands had vanished. The hypersaline lakes had been diluted to nothing, and where there had been one of the most extreme environments on Earth, there was now an ocean. Not quite the Mediterranean we know today. That would take more time, more mixing, more biological colonization, more geological settling, but recognizably a sea again after over 500,000 years of absence. The speed of it all is what makes it remarkable. 2 years, 730 days, from empty basin to full ocean, from the most dramatic act of creation through destruction the Mediterranean would ever experience. And the evidence is still there, buried beneath the seafloor, waiting for anyone willing to look. Layers of rock that record the moment when everything changed, when the Atlantic came roaring through Gibraltar and gave the Mediterranean back its soul. Now, you might be thinking, okay, that's a great story. Catastrophic flood, empty Mediterranean refilling in 2 years, most dramatic geological event in millions of years. But how do we actually know any of this happened? Because here's the thing, nobody was there with a camera. No ancient humans recorded it. This all happened 5.3 million years ago, long before anything resembling our species existed. So how can scientists possibly reconstruct something so ancient and so dramatic? The answer is written in the rocks, and the story they tell is absolutely remarkable. The first clues came in the 1970s when deep-sea drilling projects started extracting core samples from the Mediterranean seafloor. These weren't just random holes in the mud. These were systematic expeditions designed to understand the geological history of the entire basin. Scientists would drill down hundreds of meters into the seafloor, pulling up cylindrical cores of sediment that represented millions of years of accumulated material. Each layer, each change in composition, tells you something about what was happening when that sediment was deposited. And what they found underneath the normal marine sediments of the modern Mediterranean was completely unexpected. Massive layers of evaporate minerals, salt, gypsum, anhydrite, minerals that only form when seawater evaporates in shallow, isolated basins. But these weren't thin layers. In some places, these evaporate deposits were over 2 kilometers thick. 2 kilometers of salt and gypsum sitting at the bottom of what is now a deep ocean basin. Think about what that means. To create 2 kilometers of evaporate deposits, you need absolutely massive amounts of evaporation. You need seawater flowing into a basin, evaporating completely, leaving its mineral content behind, then more seawater flowing in to repeat the process. Over and over again for hundreds of thousands of years. This wasn't a sea that occasionally dried up. This was a basin that was repeatedly filled and evaporated, like some kind of geological death spiral. The composition of these evaporates tells us even more. The deepest layers contain minerals that precipitate first when seawater evaporates. Calcium carbonate and gypsum, the minerals that form when you're still dealing with relatively concentrated seawater. Higher up in the sequence you find halite, which is basically rock salt. This forms only when the water is almost completely gone, when you're dealing with super concentrated brine that's just about to disappear entirely. And in some locations, at the very top of the evaporate sequence, you find incredibly exotic minerals. Things like carnallite and sylvite, potassium and magnesium salts that only form when even the sodium chloride has precipitated out. These are the minerals of the absolute bitter end, the last chemical residue of a dying sea. But the evaporates alone don't tell us about the flood. They tell us the Mediterranean dried up, but not how it refilled. For that we need to look at what came after. Directly above the evaporate layers, often with a sharp, dramatic boundary that you can see clearly in core samples, there's a return to normal marine sediments. Clay, silt, the microscopic shells of marine plankton, everything you'd expect to find at the bottom of a healthy ocean. But here's what's remarkable. The transition is incredibly abrupt. You go from desert minerals formed in the hottest, driest conditions imaginable to deep marine sediments in what appears to be geological instant. No gradual transition, no slow return to marine conditions. Just bang, desert to ocean. This sharp boundary is exactly what you'd expect from a catastrophic flood. Sudden inundation, rapid burial of the dry surface, immediate return to full marine conditions. If the Mediterranean had refilled slowly over millions of years, you'd see gradual changes in the sediment. Shallow water deposits transitioning to deeper water deposits, evidence of shorelines migrating intermediate conditions. But that's not what we find. We find evidence of rapid, dramatic, overwhelming change. The microfossil evidence makes this even clearer. Paleontologists studying these cores can identify the tiny shells of marine organisms preserved in the sediment. Different species tell you about different environmental conditions. Some prefer warm water, some cold. Some live in shallow seas, others in deep ocean. Some can tolerate unusual salinity, others are very particular about their water chemistry. In the sediments immediately above the evaporates, you find a sudden reappearance of normal Atlantic marine species, not Mediterranean species slowly evolving in isolation, not weird brackish water species that might inhabit a slowly filling basin, full-on Atlantic Ocean species that show up all at once, as if they'd just poured in through a newly opened gateway, which is exactly what happened. Even more revealing, these species appear at the same time across the entire Mediterranean basin. Sites in the eastern Mediterranean, sites in the western basin, sites in isolated sub-basins. They all show the return of marine life at approximately the same moment in geological time. This synchronicity is the signature of a single event affecting the entire region simultaneously. If the sea had refilled slowly, you'd expect western sites to show marine life returning first, then gradually spreading eastward as the water advanced. But that's not the pattern. The pattern says everything happened at once. But perhaps the most dramatic evidence comes from the Gibraltar Strait itself. Modern bathymetric surveys using sophisticated sonar have mapped the underwater topography of the strait in incredible detail, and what they've found is evidence of erosion on a scale that's almost hard to comprehend. The channel through Gibraltar shows massive U-shaped valleys carved into the bedrock. These aren't the gentle, gradual channels formed by normal ocean currents. These are deep gouges, erosional scars that could only have been created by water moving at catastrophic velocities. Underwater channels hundreds of meters deep, carved through solid rock in what must have been an incredibly short period of time. The math here is straightforward. Rock doesn't erode easily. To carve through hundreds of meters of limestone and other sedimentary rocks, you need water flowing at tremendous speed with enormous erosional power. Normal ocean currents can't do this. Tides can't do this. Even the strongest storm-driven currents can't create this kind of erosion. You need something extraordinary. You need a waterfall carrying the combined flow of hundreds of Amazon rivers, all concentrated through a single channel, all scouring away everything in their path. Seismic surveys have revealed even more buried beneath the seafloor. Remember, we're not just looking at the surface here. Modern geophysical techniques allow scientists to create three-dimensional maps of subsurface structures, seeing layers and features buried under kilometers of more recent sediment. These surveys show extensive channel systems carved into the pre-flood surface, not just at Gibraltar, but throughout the Mediterranean basin. Channels that appear to have been cut by massive flows of water moving from west to east, from the Atlantic connection toward the deepest parts of the Mediterranean. These buried channels are now filled with more recent sediments, but they're still visible in seismic data as distinctive features with different acoustic properties than the surrounding material. The pattern of these channels tells you something crucial about how the flood progressed. They're not random, they follow logical pathways that water would take flowing downhill into the deepest basins. They show branching patterns, tributary systems, exactly what you'd expect from a massive flood spreading out and seeking the lowest elevations. This is the fossilized drainage network of the Zanclean Flood, preserved beneath millions of years of subsequent sediment. Some of these buried channels are truly enormous. We're talking features tens of kilometers wide and hundreds of meters deep. Canyons that rival anything visible on Earth's surface today, except these were carved in a geological eye blink and then buried and preserved for 3 million years. But how do we know when all this happened? How can scientists date events from millions of years ago with any precision? The answer involves multiple independent dating methods that all converge on the same timeline. First, there's something called magnetic stratigraphy. Earth's magnetic field occasionally reverses, with magnetic north and south swapping places. These reversals happen irregularly, but they leave distinctive signatures in rocks that contain magnetic minerals. As sediments are deposited, magnetic minerals align with Earth's magnetic field at that time. Later, scientists can measure these alignments and match them to the known chronology of magnetic reversals. The evaporites and the post-flood sediments in the Mediterranean contain these magnetic signatures. By matching them to the global magnetic reversal timeline, scientists can determine approximately when different layers were deposited. This puts the end of the evaporite deposits and the beginning of the marine refilling at right around 33 million years ago. Not an exact date, but close enough to establish the general time frame. Then there's astronomical tuning, which sounds like science fiction, but is actually remarkably precise. Earth's orbit isn't perfectly circular, and its axial tilt varies slightly over long time scales. These variations, called Milankovitch cycles, affect how much solar radiation different parts of Earth receive, which influences climate. Climate changes leave signatures in sediment, variations in the types of minerals deposited, changes in the species composition of microfossils, chemical markers that indicate temperature or rainfall. By identifying these cyclical patterns in Mediterranean sediments and matching them to the calculated orbital parameters of Earth over the past several million years, scientists can calibrate their age estimates with remarkable precision. Astronomical tuning has refined the date of the Zanclean Flood to 33 million years ago, give or take about 10,000 years. That's incredibly precise for an event so ancient. Additional confirmation comes from radiometric dating of volcanic ash layers, occasionally found in Mediterranean sediments. When volcanoes erupt, they deposit ash layers that can be dated using radioactive isotope decay. These ash layers act as time markers, anchoring the relative timeline established by magnetic stratigraphy and astronomical tuning to absolute dates measured by atomic decay. All of these independent methods converge on the same answer. The Mediterranean desiccation crisis ended with a catastrophic flood approximately 33 million years ago. The precision of modern dating techniques means we can be confident in this timeline, even though the events happened long before human observation. But here's where the story gets even more interesting. The more scientists study the evidence, the more complex the picture becomes, because it turns out the Zanclean Flood might not have been a single event. Some evidence suggests multiple episodes of flooding, perhaps an initial breach at Gibraltar that partially refilled the Mediterranean, followed by additional collapses that completed the process. Certain sediment cores show what appear to be multiple flooding horizons, layers that suggest rapid water level rise separated by brief intervals of stability or even slight retreat. This has sparked ongoing scientific debate. Was the flood one continuous 2-year deluge, or was it a series of catastrophic episodes spread over a longer period? Did Gibraltar breach Gibraltar once catastrophically, or were there multiple breaches as different parts of the natural dam failed at different times? The truth is, we don't know for certain. The geological evidence is consistent with both scenarios. A single massive flood would leave similar signatures to a series of closely spaced floods. The time resolution of our dating methods, while incredibly precise by geological standards, isn't quite good enough to distinguish between events separated by only decades or centuries at this time depth. Some researchers have proposed that the initial breach might have only partially filled the Mediterranean, perhaps to several hundred meters below the Atlantic level. Then a subsequent breach, maybe centuries later, completed the flooding. This would explain certain anomalies in the sediment record, layers that seem to suggest a pause in the flooding process. Others argue that the evidence is more consistent with a single, continuous flood. They point out that the erosional features at Gibraltar suggest sustained, high-velocity flow, not multiple separate events. They note that theoretical models of dam collapse typically predict that once a breach begins, it rapidly progresses to complete failure. Partial breaches followed by temporary stability, they argue, are less physically plausible. This is how science works. The big picture is clear. The Mediterranean dried up and then catastrophically refilled. But the precise details, the exact mechanism, the timeline of the event, these are being continuously refined as new evidence emerges and new analytical techniques become available. Recent studies using high-resolution seismic imaging have revealed even finer details of the buried flood channels. Computer modeling of the fluid dynamics involved keeps getting more sophisticated, allowing researchers to test different scenarios and see which ones best match the geological evidence. New core samples from previously unstudied locations add data points that either support or challenge existing interpretations. What's remarkable is that all of this evidence, these evaporates, these erosional channels, these microfossil assemblages, these magnetic signatures, They've been sitting at the bottom of the Mediterranean for over 5 million years, waiting for someone to develop the technology to find them and the knowledge to interpret them. The rocks remember everything, every flood, every drought, every catastrophe. They record it all in layers of sediment, in chemical compositions, in the fossils of organisms that lived and died and left their shells to tell the story. And the story they tell is one of the most dramatic geological events in Earth's recent history. A sea that vanished and returned in a flood so vast it defies easy comprehension. The evidence is there, buried but not forgotten, waiting for each new generation of scientists to extract just a little more detail, to refine the timeline just a little more, to understand just a little better what happened when the Atlantic Ocean finally broke through and the Mediterranean was reborn. So here's where we stop thinking about the Zanclean Flood as just this incredible spectacle, this 2-year event that filled an ocean basin, and start thinking about what it actually meant. Because 3 million years later, we're still living with the consequences. The Mediterranean you see today, the one with cruise ships and beaches and ancient civilizations built along its shores, that Mediterranean exists because of what happened when the Atlantic came crashing through Gibraltar. Let's start with the most obvious impact. The Mediterranean got deeper, permanently. Before the flood, when the basin was slowly filling with whatever water could trickle in from rivers and occasional Atlantic breakthroughs, it was shallow. We're talking about a sea that, in its pre-crisis form, was maybe 500 to 800 meters shallower than today in some areas. The Messinian crisis had evaporated all that depth away, turned it into salt deposits kilometers thick. When the flood refilled the basin, it didn't just restore the old shorelines. It actually created a deeper, more voluminous Mediterranean than had existed before the crisis. Because here's the thing, during those 630,000 years of desiccation, the Mediterranean basin hadn't just been sitting there empty and waiting, it had been subsiding. The Earth's crust beneath the basin was slowly sinking under its own weight, responding to tectonic forces that didn't care whether there was water there or not. So when the Atlantic finally broke through, it was filling a depression that was actually deeper than the original Mediterranean had been. In some places the new sea was 200, 300, maybe even 400 meters deeper than its predecessor. That might not sound like much when you're talking about an entire ocean basin, but think about what that means in practical terms. You've just added thousands of cubic kilometers of water permanently. You've created a whole new vertical dimension to the marine ecosystem. Deep water environments that didn't exist before suddenly became available for colonization. And colonize they did. This is where the story gets really wild from a biological perspective. When the flood happened, it wasn't just water pouring in through Gibraltar, it was an invasion. Every marine species in the Atlantic that could survive the journey through that churning, violent strait suddenly had access to an entirely new ocean. Thousands of species poured in with the floodwaters: fish, marine mammals, invertebrates, plankton, algae, everything. It was the greatest single colonization event in marine history. But they weren't colonizing a pristine, empty environment. The old Mediterranean, the one that had existed before the crisis, had its own endemic species. Communities that had evolved in isolation for millions of years adapted to the specific conditions of that ancient sea. When the basin dried up, most of them went extinct, but not all. Some species survived in isolated salt lakes, others retreated to the Black Sea or the few permanent water bodies that remained. When the flood refilled the basin, these survivors came back. What happened next was like watching evolution in fast forward. You had Atlantic species adapted to one set of conditions, meeting Mediterranean survivors adapted to something completely different, all competing for resources in a newly created environment. Natural selection went into overdrive. Within thousands of years, maybe tens of thousands, the Mediterranean developed a completely new ecosystem, a hybrid community combining Atlantic colonizers with Mediterranean survivors, all evolving rapidly to adapt to local conditions. This ecosystem structure is still visible today. If you're a marine biologist studying Mediterranean species, you can often trace their ancestry back to one of two sources. Either they're descended from Atlantic colonizers that came through after the flood, or they're descended from pre-crisis Mediterranean species that somehow survived the desiccation. The genetic signatures are still there, written in the DNA of every fish and mollusk and coral in the sea. They're all descendants of flood survivors, every single one. But the flood's impact wasn't confined to the Mediterranean basin itself. What happens in the Mediterranean doesn't stay in the Mediterranean. The refilling changed climate patterns across 3 continents, because suddenly you had this enormous body of water sitting in the middle of what had been a giant hyper-arid desert basin. And water, as we've discussed, changes everything. First, there's the humidity issue. An ocean basin full of water is constantly evaporating. The Mediterranean today sends something like 3,600 cubic kilometers of water into the atmosphere every year. That's water vapor that gets picked up by wind patterns and distributed across southern Europe, North Africa, and the Middle East. Before the flood, when the basin was a salt desert, that moisture source didn't exist. The regions surrounding the Mediterranean were probably 20, 30, maybe even 40% drier than they are today. When the sea refilled, rainfall patterns across the entire region shifted. Areas that had been extreme desert began receiving regular precipitation. Vegetation zones migrated. Rivers that had been struggling to flow with anything more than a trickle suddenly had reliable water sources feeding them. The entire climate regime of southern Europe and North Africa reorganized itself around this newly restored moisture source. And it happened fast, not geologically fast, actually fast. Climate models suggest that within just a few decades of the basin filling, regional precipitation patterns had completely reorganized. Plants that could exploit the new moisture moved in. Animals that depended on those plants followed. Within a few thousand years, the entire ecological structure of the Mediterranean region had transformed. But here's where it gets really interesting, where the story reaches across continents and ties into something completely unexpected: human evolution. Because the Zanclean Flood didn't just change the Mediterranean climate, it triggered a cascade of atmospheric and oceanic changes that affected global climate patterns. And some of those changes hit East Africa right at a critical moment in human evolutionary history. Now, we have to be careful here. We're not saying the flood caused human evolution. That would be ridiculous oversimplification. But climate scientists studying this period have found something intriguing. The refilling of the Mediterranean altered ocean circulation patterns in the Atlantic. That changed how heat was distributed between the northern and southern hemispheres, and that through a series of complex atmospheric teleconnections that we're still working to understand fully, seems to have influenced monsoon patterns in East Africa. Right around the time of the Zanclean Flood, maybe within a few 100,000 years, East African climate began showing increased variability, wetter periods alternating with drier periods on timescales of thousands to tens of thousands of years. This climate instability, This constant environmental uncertainty created exactly the selective pressures that evolutionary biologists think drove early human evolution. The need to adapt quickly to changing conditions, to develop larger brains capable of problem solving and innovation, to create social structures that could maintain knowledge across generations. We can't draw a straight line from the flood to human intelligence. Evolution doesn't work that way. But we can say that the Mediterranean refilling was part of a global climate reorganization that included East Africa, and that reorganization happened right when our ancestors were developing the traits that would eventually make us human. It's not causation, but it's probably not coincidence either. The flood's impact is also written in the rocks, literally carved into the geology of the Mediterranean seafloor. When all that water came pouring through Gibraltar, it didn't just fill a basin. It carved canyons, deposited sediments in specific patterns, created geological features that are still visible today if you know what to look for. Modern seafloor mapping has revealed massive underwater channels running from Gibraltar across the Mediterranean basin. These aren't river channels, they're flood channels. The erosional scars left by 100 million cubic meters of water per second forcing its way through the strait and then spreading across the basin floor. Some of these channels are hundreds of meters deep, carved into solid rock by the sheer hydraulic power of the floodwaters. The sediment distributions tell the story too. Before the flood, the Mediterranean basin had accumulated those thick evaporate deposits, the salt and gypsum layers kilometers deep in places. The floodwaters disturbed these deposits, eroded them in some areas, buried them under new marine sediments in others. When geologists take sediment cores from the Mediterranean seafloor, they can identify the exact boundary layer marking when the flood happened. Below it, evaporates and continental sediments. Above it, normal marine deposits. It's one of the most dramatic geological transitions visible in the Earth's sedimentary record. These cores also show something else fascinating. The flood didn't fill the basin uniformly. The deepest parts filled first, obviously, but then there was this complex pattern of sediment deposition as the water level rose. Turbidity currents, massive underwater avalanches of sediment-laden water, swept across the basin floor as the flood progressed. These currents deposited sediment layers that can be traced across hundreds of kilometers of seafloor. Each layer represents a different phase of the filling process, a snapshot of what the floodwaters were doing at that particular moment. For modern geologists, the Zanclean Flood is like a natural laboratory for understanding catastrophic processes. We don't get to observe events like this in real time, obviously. Human civilization has only existed for maybe 10,000 years, and nothing remotely comparable to the Zanclean Flood has happened during that time. But we can study its geological aftermath, use that evidence to develop models of how catastrophic flooding works, and then apply those models to other situations. This isn't just academic curiosity. Understanding how massive rapid water transfers affect landscapes and ecosystems has direct applications to modern concerns. Because we're living in a time when water levels are changing again, not as dramatically as the Zanclean Flood, not even close, but changing nonetheless. Sea levels are rising as global temperatures increase, ice sheets are melting, ocean circulation patterns are shifting. By studying what happened when the Mediterranean refilled, scientists gain insights into how marine ecosystems respond to rapid environmental change. They learn about the timescales involved in ecological reorganization. They develop better models for predicting how coastlines will evolve as water levels change. They understand more about the relationship between ocean basins and regional climate. The flood also teaches us something more philosophical, something about the nature of geological time and planetary change. The Mediterranean feels permanent. If you're standing on a beach in Greece or Spain or Tunisia, looking out at that blue water stretching to the horizon, it seems like it's always been there. Ancient civilizations rose and fell on its shores. Homer wrote about it 2,800 years ago, and it was ancient even then. But it's not permanent. 5. 3 million years ago it didn't exist. Not as a sea anyway. It was a desert, the driest place on Earth, a hell landscape of salt pans and scorching temperatures. Then, in just 2 years, it transformed into an ocean. That's the kind of change that rewrites our understanding of what permanent means on a planetary scale. Even major geographic features, things as large as ocean basins, exist in a state of constant flux on geological timescales. The Mediterranean has dried up and refilled multiple times in its history. The Zanclean Flood was just the most dramatic refilling event, but probably not the only one. Tectonic forces are still working today, still pushing Africa toward Europe, still working to close the Strait of Gibraltar. In another few million years the strait might seal again. The Mediterranean could dry up again, or Africa and Europe might fully collide, turning the Mediterranean into something completely different. Maybe an inland sea like the Caspian or Black Sea. This impermanence extends to everything about our planet's surface. Mountain ranges rise and erode away. Continents drift across the globe, colliding and fragmenting. Ocean basins open and close. The Earth's surface is in constant motion, constantly reorganizing itself according to the deep forces of plate tectonics and the surface forces of erosion and deposition. We humans exist on these surfaces during a geological eye blink. Our species has been around for maybe 300,000 years, modern civilization for maybe 10,000. The Mediterranean in its current form has existed for 3 million years. We're newcomers, latecomers to a landscape shaped by processes that dwarf our entire existence as a species. But here's the thing. We can understand these processes. We can read the story in the rocks, trace the evidence in sediment cores and underwater canyons, use chemistry and physics and biology to reconstruct events that happened millions of years before anything resembling a human existed. That capacity for understanding, that ability to piece together ancient history from fragmentary evidence, that's uniquely human. That's the product of those big brains that evolution gave us, possibly influenced by the same climate changes that the Zanclean Flood helped set in motion. The flood also reminds us about the interconnectedness of Earth systems. What happens in one region doesn't stay in one region. The Mediterranean refilling changed Atlantic circulation. Atlantic circulation changes affected global climate. Global climate changes influenced evolution in Africa. Evolution in Africa eventually produced humans capable of studying and understanding the flood that helped shape the climate that influenced their evolution. It's all connected, all part of one vast, complex system operating across millions of years. And finally, the flood teaches us about resilience and recovery. The Mediterranean didn't just recover from the Messinian crisis. It came back different, deeper, with a new ecosystem, new climate impacts, new geological structures. But it came back. Life recolonized the basin. Ecosystems reorganized. The water found its level, and the world adapted. This pattern of catastrophe, followed by reorganization and recovery, is fundamental to Earth's history. The planet has experienced mass extinctions, climate catastrophes, impact events, supervolcanic eruptions. Every time, life recovers. Not the same life, not the same ecosystems, but life nonetheless. The Zanclean Flood is just one example of this resilience operating on a regional scale. 5.3 million years later, the Mediterranean is one of the most biologically diverse marine regions on Earth. Its shores host dozens of countries, hundreds of millions of people, and thousands of years of human civilization. None of that would exist in its current form if the flood hadn't happened. The entire modern Mediterranean world, everything about it, is built on the geological foundation created when the Atlantic broke through Gibraltar, and 2 years of deluge rewrote the map of Europe and Africa. That's the lasting impact. Not just changed geography or new ecosystems or altered climate patterns, though those are all important. The real impact is that we live in a world shaped by that event, whether we realize it or not. The food webs in the Mediterranean, the weather patterns across southern Europe, the underwater geology of the entire basin, they're all flood legacies, still present, still influencing the planet 3 million years later. Because here's what events like the Zanclean Flood teach us. Earth's history isn't a series of static scenes. It's a continuous process of change, sometimes gradual, sometimes catastrophically rapid. The Mediterranean you could visit today is just one frame in a much longer film, one moment in an ongoing story of planetary evolution. And that story is far from over. So here we are, at the end of a story that spans nearly 1 million years. From a thriving, ancient sea filled with life to a desert basin deeper than the Grand Canyon, then back to an ocean in just 2 years. The Zanclean Flood, the Mediterranean's resurrection, one of the most dramatic geological events in Earth's recent history. Think about the journey we've traced. 96 million years ago, the Mediterranean was a normal sea. Ships could have sailed from Spain to Egypt if ships had existed. Fish swam in waters a mile deep. Coastlines teemed with life. Then the connection to the Atlantic closed. Maybe an earthquake, maybe shifting tectonic plates, maybe just gradual uplift of the Gibraltar threshold. But once that connection broke, physics took over. The Mediterranean receives less water from rivers than it loses to evaporation. Without Atlantic inflow, it had no choice but to evaporate, and it did, catastrophically. Over perhaps a few thousand years, an entire sea evaporated into desert. Water levels dropped 10 feet per year. Coastlines retreated miles annually. Rivers that had flowed gently into the sea became waterfalls plunging thousands of feet into the shrinking basin. Species that had evolved over millions of years went extinct in generations. The Mediterranean became a hell of salt flats, brine pools, and scorching temperatures, a desert covering an area the size of India, sitting where an ocean had been. For 640,000 years, this continued. The Messinian Salinity Crisis. 640,000 years of salt accumulation, of river canyons cutting deeper and deeper into bedrock, of a wound in the Earth's surface that grew wider and more desolate with each passing millennium. The planet had seen nothing like it before or since. But geology never stops moving. The same tectonic forces that had closed Gibraltar were still grinding away. And eventually, around 33 million years ago, something shifted. Maybe a single earthquake that dropped the Atlantic threshold by a few meters. Maybe gradual erosion that finally breached a critical point. We'll never know the precise trigger, but we know what happened next. Water began flowing through Gibraltar. Not much at first. Maybe a small waterfall, maybe a series of rapids. But water is patient and relentless. Every drop that fell into the Mediterranean carried tiny particles of rock, eroding the channel just a little bit deeper, and as the channel deepened, more water could flow. And more water meant more erosion. Positive feedback. The kind of geological process that starts slow and ends in catastrophe. Within months, maybe weeks, that small breach became a torrent. Within a year, it became the largest waterfall in Earth's history. 10,000 times the flow of Niagara. A curtain of water 200 kilometers wide, thundering into the basin with the force of 1,000 hurricanes. The noise would have been audible hundreds of miles away, a constant roar that drowned out every other sound. The mist would have created its own weather systems, storms that never ended, fog that covered the entire basin, and the Mediterranean rose, 10 meters per day at the peak flow, coastlines advancing miles in a single day, salt flats that had baked under the sun for 640,000 years vanishing beneath the waves in hours. Species that had adapted to the hypersaline conditions drowning as their world transformed around them. For 2 years this continued. 90% of Earth's river water flowing through a single channel, the ocean's revenge on the desert that had dared to exist where a sea belonged. Then it was over. Water levels equalized. The Mediterranean and Atlantic reconnected as equals. The catastrophic flow slowed to a normal tidal exchange. The greatest geological event in recent Earth history ended as suddenly as it had begun, leaving behind only evidence. Salt deposits kilometers thick, underwater canyons carved into bedrock, pebbles transported hundreds of miles by the flood, and above it all a new coastline, the shores we recognize today as the Mediterranean Sea. But here's what gets me about this story. It's not that the flood happened, it's that we figured it out. No human witnessed the Zanclean Flood. It happened over 5 million years before our species evolved. But through geology, through patient examination of rock layers and salt deposits and underwater canyons, we reconstructed the entire sequence of events. We can tell you how fast the water flowed, how long the refilling took, even what the temperature was during the crisis. That's the power of science, the ability to read stories written in stone, to decode events so ancient and so vast that they would seem unknowable. The Mediterranean today conceals all of this. Tourists sun themselves on beaches where megafloods once raged. Ships sail peacefully over canyons carved by catastrophic water flow. The salt mines of Sicily and Cyprus are harvested for table salt, remnants of an ocean that evaporated 5 million years ago. None of them know the violence that created the world they're enjoying, the desperate years of evaporation, the unimaginable power of the refilling. And maybe that's appropriate, because Earth has a way of healing its wounds, of smoothing over catastrophes and creating new normalcy. The Mediterranean survived being a desert. It survived being refilled by the greatest waterfall in history. Now it sits peacefully in the sun, as if none of it ever happened. If you've enjoyed this journey through deep time, this exploration of one of Earth's most dramatic geological events, go ahead and hit that like button. It helps more people discover these stories written in stone. And I'm curious, where are you listening from right now? Did this video help you sleep? Or did the scale of the Zanclean Flood keep you awake thinking about the power of our planet? Drop a comment and let me know. If you want more content like this, more deep dives into Earth's violent past told in a voice meant for relaxation, hit that subscribe button. There are more stories waiting. Ice ages that nearly froze the entire planet, supervolcanoes that darkened the sky for years, asteroid impacts that reshaped continents, all of them just as dramatic as the Mediterranean's resurrection, all of them just as perfectly preserved in the geological record. But for now, rest easy. The Mediterranean remembers. Even if we forget, the rocks remember everything.